Let's get started with the first talk of the session. The speaker is Paul Dellar from University of Oxford, and he will speak about discrete divergence-free conditions in lattice Boltzmann magnetohydrodynamics, a data-driven approach. So please.
Thank you very much for the introduction. So I'm going to I'm going to talk as a quick overview of lattice Boltzmann magnetohydrodynamics. This is about solving equations for a fluid coupled with Maxwell's equations. Maxwell's equations ought to preserve the divergence of the magnetic field being zero. So I'll look at what we can say about the magnetic field on the lattice, what conditions it satisfies, using the kind of data-driven approaches that we heard about yesterday evening based on simulation output. And that's going to suggest an interesting hypothesis, which I can then establish doing some theory. So MHD, it's a single fluid description of fluids or gases with two kinds of charged particles. So liquid metals, electrolytes, ionized gases or plasmas. So you might be interested in these equations. You're interested in simulating nuclear fusion, processing liquid metals, making aluminium, or interested in interiors of planets, stars, or forecasting so-called space weather around the Earth to make sure satellites don't get chewed up by radiation coming from the sun. So I'm going to think about phenomena where the fluid velocity is always small compared to the speed of light. So Maxwell's equations boil down to these pre-Maxwell equations. Magnetic field B evolves through the curl of an electric field, but the electric field appears nowhere else. We just have div B is 0, J is, so it's just being weird, never mind. J is curl B. So the electric field is just a flux of B in the sense of a conservation law. And I'm going to rewrite this Maxwell equation like this is the divergence of a thing I call lambda. And if lambda is an anti-symmetric tensor built out of E, that's exactly the same as Maxwell's equations. So that's how Maxwell's equations work for things moving slowly compared to the speed of light. So to build the MHD equations, I have a Lorentz force J cross B, which says how the magnetic field acts on the fluid, and then an Ohm's law, which says how the electric field is related to the fluid velocity U, and a bit of diffusion. So down here at the bottom, I have the induction equation that says if eta was 0, B just gets advected around by the fluid in a spatial way for vector fields, and eta gives me a little bit of diffusion. And then there's the Lorentz force J cross B, which has the magnetic field acting on the fluid. Okay. So I want to simulate those. And the problem is, if we do lattice Boltzmann hydrodynamics, so we build a momentum flux from the second moment of a scalar distribution function, we get the momentum evolves through the divergence of a symmetric momentum flux. That's good for angular momentum conservation. It's a disaster for doing Maxwell's equations. We want this thing to be anti-symmetric instead of symmetric. So the usual kind of lattice Boltzmann approach of scalar distribution functions won't work. So instead, what I'm going to do is to say, well, let's suppose we have distribution functions that are themselves vectors. So think about populations of little bar magnets flying around and colliding. And then if I define my magnetic field B to be just the 0th moment, the sum of the G's, and the lambda to be the first moment, and now this is the xi vector, the particle velocity, this is the G itself a vector, so there's no reason why this should be symmetric, and I can derive this, which is going to be my magnetic field evolution equation. Why doesn't want to keep moving? Come on. So the screen's just stuck. Is that okay? I know that's not as good, but I can at least make it go forwards and backwards. You still see my window?
Yes, it's okay. Yeah, sure.
So you say this is crazy. The G's are vectors, the F's were scalars. This is much worse, but we don't need as many discrete velocities because we don't need such high moments. In fact, if we stop at the second moment, this thing M, that down there, that's going to be enough. So in 2D, I just need 5 velocities in this sort of red color instead of the 9 I would use for the fluid. And in 3D, I would just use 7 velocities for the magnetic field instead of, well, 15 is a bit dated now, 19 or 27 for the fluid. So I've got a set of moments, B, lambda, and this thing I call M, which looks like it's got too many elements, except it's 0 unless the first two indices are the same, because there are no discrete velocities going along diagonals in my magnetic velocities, just these reddish pink ones. Okay, so now to get the MHD equations, I'm going to have some weights and a constant theta, which goes to that 5 velocity lattice. My G looks like a normal equilibrium, except it's only got the first two terms. I pop in my lambda 0 to be U times B minus B times U the other way round, pop that in, and I get this thing with the divergence, which unpacks the B curl U cross B. So I've got ideal MHD. Now, if I do a Chapman-Enskog expansion for small relaxation times, the first correction to lambda is this no longer anti-symmetric thing involving the gradients in the magnetic field. So if I pop that in, I get resistive MHD. Resistivity eta is this constant theta times the relaxation time, just like the viscosity in lattice Boltzmann hydrodynamics. This thing lambda is a consistent proxy for div B, because trace lambda is some multiple of div B plus a very small term, because the first correction actually vanishes. But you might ask, well, what can we say about B on the grid, on the lattice, as well as about this extra new kinetic variable called lambda? Also, we need B on the lattice to put it into the momentum flux for the hydrodynamic part in order that we can make the fluid move around. So you just change the equilibrium momentum flux so that the second moment is this, and you've got MHD. So now what I want to ask is, okay, what happens on the grid? So we know if we simulate that trace of lambda is preserved near 0, but what about B? So if we're doing 2D, I think about this blue point in the middle, I can naturally form two different finite difference approximations of the second order accurate. I can use the points on the axes, that's these red ones, gives me this formula. I can write it as a sum over magnetic field displaced by one of these 4 directions, or I could use the points on the diagonals marked in the green, and then I get this new sum over these 4 points displaced by distance root 2. And if I'm constrained to have 90-degree rotational symmetry, I must have a linear combination of those two. That's the best I can get. So let's look at ask what linear combination of these two things, the delta plus is with the axes, the delta cross is the diagonals, using simulation output. So I'm going to run MHD simulations. I'm going to compute the RMS value of this linear combination of the two divergences, and it's going to be minimized at this value theta min, which I can work out from the simulation data. So let's do that. Here's the simulation. So it's a smooth MHD flow that winds itself up. So you get an intense layer of vorticity and current, not so intense because my resistivity is quite big at the moment. And then if I use the diagonal, the delta plus, I get a divergence that's about 5 times 10 to the minus 3. Whereas if I take an optimal value, I get something that's more like 10 to the minus 6. So it's much, much smaller if I pick the optimal finite difference stencil versus the naive one on the diagonals. And here's just a plot showing the current at 3 different time levels, and I'm doing a scan in theta. How big is my linear combination of the two divergences as a function of theta? There's a very pronounced minimum at some value of theta that's nearly a half, and that stays in the same place as the simulation evolves. So at least it's robust for the time evolution. Now I can also do, yeah, that's that same plot again, bigger. Minimum seems to be in the same place for these 3 different time levels. I also do a scan in Tor, and then as Tor changes, the location of the minimum changes. So it's moving to smaller values of theta as Tor gets bigger. So this is, again, as somebody was saying yesterday, cheap GPU simulations, I can do these kinds of parameter sweeps and find out what's happening. So then I'm really brave and say, let's just do lots and lots of simulations, different values of Tor, work out the value of theta, that interpolation parameter that minimizes the divergence, and I get a beautiful fit to this formula that says the best finite difference combination has this parameter theta, which is a half 1 minus 4 times the magnetic relaxation time squared. I'm afraid I'm being quite sloppy about taking out my factors of delta t. So that's Tor in lattice units. So that's very interesting. How are we going to understand that? Also, the optimal combination, that's in blue, is much smaller than either alone. either along the axes or along the diagonals, that at the moment it's still much bigger than the trace of the lambda, that kinetic variable. Okay, so there's an interesting hypothesis that says this is a good value of theta. Why should that be? Well, this is a bit of a mess, I'm afraid, but if we take the lattice-Boltzmann scheme, write it like this in the top line, so the twiddle means a post-collisional distribution, and then we slide it to an adjacent grid point at a later time step. If I take moments of that lattice-Boltzmann scheme, I can get update rules for the moments, which I can write like this. So the x's and the x bars are differences and averages on adjacent points, and similarly for y and y bar. And these operators all commute, because if I've got a domain with periodic boundary conditions, I can diagonalize all of them simultaneously with a discrete Fourier transform. They satisfy these nice little relations about the square of the average being identity plus the square of the difference. So I can eliminate and express my m's in terms of my lambdas. That's the electric field tensor. And now I can write the lambdas as a horrible long expression involving just the lambdas at different time levels and x operating on the x components of B. Similarly for y operating on the y component of B. And I dump it in to my linear combination of the two divergences. That's this top thing. And I get a terrible, great big mess involving both the trace of the lambda and the trace that's part of the difference of the diagonal entries. That's the A thing. And in this horrible long mess, there's this red term which multiplies the A by itself, as opposed to differences between A's at different time levels. So what I want to do is to choose theta to kill off this red term. And that's what gives me the formula I showed you earlier, a half minus a quarter tau squared when you untangle it all. So you can do analysis that says this is the right theta to use, but this is a piece of analysis I think nobody would have done without that brute force scan the simulation output to say there is something interesting here, let's go and find out what it is. And now, because these involve time derivatives, if we go particularly to diffusive scaling, so we're dropping the time step, fasten the grid spacing in order to converge in incompressible limits, then my optimal value of the divergence is actually going to zero like the fourth power of the grid spacing, whereas the ones based on just the axes or just the diagonals only going like the second power. So they're consistent, they're converging to zero. The optimal one is both much smaller and converges with fourth order instead of second order. Okay, I can do the same thing in 3D. It's even more horrendous. Now I've got three terms I can have. I can go to points on the axes, points distance √2 apart, or points distance √3 apart. So I've got a theta and a phi, same parameters. Again, now, yeah, it's ridiculous. From a few years ago, I can do 3D simulations cheaply enough to do these parameter scans in Tor. Then the red simulation data fits this function very nicely, and the blue for the phi simulation data fits this function very nicely. You can do the same kind of analysis I showed you, even more of a mess, to find out what these are. So this gives me the optimal approximation to the discrete divergence in 3D. Again, started off by fitting simulation output to find what was best, then doing theory to back it up. So just to sum up, what we do in the lattice-Boltzmann world is we take the system we want to solve, in this case, the induction equation, we embed it in a bigger linear constant coefficient hyperbolic system whose slowly varying solutions satisfy the equations we want, but it's not always obvious how the scheme with all these extra kinetic variables behaves at the scale of the lattice. We know that in MHD for lattice-Boltzmann, the trace of this lambda thing is approximately zero, so that's the consistent kinetic approximation. But what about B on the grid, particularly if you wanted a couple to use MHD as part of some bigger, more complicated system, you might care about that. A brute force search saying, let's try all plausible stencils, what gives us the smallest divergence, picks out this value of theta, which I've backed up with a theoretical analysis. And it's interesting because if you untangle this, it says that we almost take the average of along the axes and along the diagonals, but not quite. There's a little tau squared correction. This is reminiscent of doing bounce back boundary conditions. That places the boundary almost halfway between grid points, but it shuffles a little bit. It depends on tau. So I've done the same kind of analysis. How does the right place depend on tau? It's almost halfway, but not quite. And then the interesting thing is, because this linear combination is so much smaller, either one alone, the divergence computed on the axes is almost exactly minus the divergence computed on the diagonal. So that's kind of weird that the two finite difference stencils give you almost exactly opposite answers. That's not a sign error, that's really true. So overrun a little bit, I'm sorry, and thanks very much.
Thank you, Professor Della, for the nice presentation. So we are open to questions. If you have any, please. We have about 5 minutes, so good amount of time.
While people are having a think, I just looked back and what I'm doing now, I realize it's 1,000 times faster than when I first started doing these back around 2000. But then if you got an MLUP, you were happy. And this is running about 2,000 MLUPs on a GPU. So that's really enormous difference. Stuff that used to take a week, I can now just do in a few minutes.
Yeah. Okay, so if there are no questions, I think we can thank Professor Della for the talk, and I think we can move to the next one. So we, in the end, could principally anticipate a little bit coffee break. Thank you, Professor Della.
Thank you.
So the next speaker, let me give the rights, is I think should have the right to share the screen now. Is UG.
Yeah.
Yeah. So UG from University of Tsinghua, I think. Correct me if I'm wrong. She will speak about three-dimensional multiple relaxation time, discrete Boltzmann model, or compressible reactive flows. So please.
Okay, I will introduce my work on the 3D multiple relaxation time DPM of compressible reactive flows from the following 4 parts. First, I will give a brief introduction on reactive flows. The reactive flows are very common in nature and industry. However, the numerical simulation of reactive flows is challenging due to the reason that the reactive flows always suffer from high compressibility and combustion instability, sometimes in a very complex geometry. In addition, the reactive flows are always accompanied by the hydrodynamic and thermodynamic non-equilibrium effects, which may play an important role in some cases. Also, the reactive flows cover a wide range of spatial and temporal scales, which also makes the numerical simulations difficult. The numerical simulation of reactive flows can be divided into 3 groups: the macroscopic methods and the microscopic methods, like the molecular dynamic, have their own disadvantages. Instead, the mesoscopic method, especially the lattice Boltzmann method, which is also called the LBM, can naturally couple complex physical processes of different levels, and is a very potential method to simulate the reactive flows. The standard LBM is obtained by discretizing the continuous Boltzmann equation and where the time step and the space step are coupled together. It consists of 2 stages, which are known as propagation and collision. The discrete equilibrium distribution function is obtained by a small truncated velocity of the Maxwell distribution function. However, this method is limited to low Mach number flows. In order to use the LBM to solve the reactive flows, the key is how to describe the energy and species field and consistently couple them. The current LBMs for reactive flows have developed two kinds of models: the hybrid method and the pure LBM formulation. In the hybrid lattice Boltzmann model, the flow simulation is accomplished through the weakly compressible LBM solver, while the energy and species field are solved by a finite difference scheme using the NS equations. According to the above introduction, we know due to the use of the discrete equilibrium distribution function, this model is limited to the weakly compressible flow. And due to the different solver for the flow field and the energy species field, this method loses the simplicity and the parallel efficiency of the LBM. Different from the hybrid method, the pure LB simulation uses a double distribution function to represent the flow field and the energy field. However, this method assumes that the chemical reaction doesn't affect the flow field. So this method cannot solve the variable density. Instead, we want to develop an LBM for the high Mach number flows and can couple the hydrodynamic and the thermodynamic fields consistently. Also, to make the best of the LBM as the kinetic model, which is beyond the conventional simulation method. This model is able to capture the non-equilibrium effect. We call this this spatial lattice Boltzmann model, the discrete Boltzmann model, which is also known as the DBM. Now I'm going to introduce the DBM from the following points, which distinguish the DBM from the LBM. Instead of solving the standard LBM equation, we directly solve the continuous Boltzmann equation. Here we use the we construct a multiple relaxation time model so that the prime number is adjustable. The elements of the relaxation matrix controls the kinetic moments approaching the equilibrium part and are related to the viscosity and other hydrodynamic coefficients. Different from the standard LBM, the space step and the time step are decoupled by using the finite difference scheme to solve the continuous lattice Boltzmann equation. Here we use the NND scheme for the spatial discretization and the third order Roncoulda method for the temporal discretization, so that we can capture the discontinuity. Also, in order from the trapezoidal analysis, we can recover the microscopic equations from the Boltzmann equation. However, to recover the NS equations, we have to satisfy the following 7 kinetic moments. As we can see in the energy equation, we introduce additional parameter I to represent the non-translational degree of freedom, so that the specific heat ratio can be adjusted by adjusting the parameter I. Also, the discrete the discrete distribution function changes by introducing the non-equilibrium by including the molecular rotation or the internal vibration energies. There are two methods to construct an equilibrium distribution function. First one is directly from the Maxwell distribution. We expand this distribution on a small velocity. However, this method is limited to low Mach number flows, as we talked about before. So we directly obtain the discrete equilibrium distribution function from the satisfied kinetic moments. These are the kinetic moments that need to be satisfied to recover the NS equations. Actually, we can describe these kinetic moments by the matrix form. And then we can obtain the discrete equilibrium distribution function by multiplying the kinetic moments by the inversion of the transformation matrix, so that we can obtain the equilibrium distribution function. This method is suitable for high Mach number flows and is more accurate. The most important part is the reaction term. Here we directly add the reaction term to the right side of the Boltzmann equation. There is a mistake. We know in chemical reaction, the chemical reaction time is much longer than that of the kinetic process, so that the distribution function, the changes of the distribution function due to the chemical reaction can be treated as the equilibrium distribution function change rate. Also, we know in the chemical reaction, the mass density or the hydro velocity is affected while the temperature changes with the chemical energy transformed into the release. So we can obtain the temperature after the chemical reaction according to the relation between the energy and the temperature. The change rate of the energy is rho times Q times lambda prime. Here, rho indicates the chemical heat release per unit mass of fuel, and lambda is the mass fraction of chemical product. In terms of the chemical reaction model, we consider a two-step reaction model to describe the induction progress and the heat release progress of the chemical reaction. Also, in the kinetic moment satisfied, we can find if we replace the FEQ by the left side and the right side is equal. This is because the conservation law. However, if replacing the FEQ with the F may lead to the imbalance between the left side and the right side. This difference is the departure of the high order kinetic moments from their equilibrium part, and can be utilized to investigate the non-equilibrium effects. From the Chapman square analysis, we can recover the we can recover the microscopic equations. However, in order to recover the NS equations, we have to add an additional term to modify the collision term so that the NS equations can be recovered accurately. Then from the Chapman's Coco expansion, we can obtain the NS equations. The dynamic viscosity and other hydrodynamic and thermodynamic coefficients are related to the elements of the matrix form and is a free parameter I. We want to construct the transformation matrix. First, we have to construct the discrete velocity model. Here, there are a total 30 kinetic moments that should be satisfied in the three-dimensional cases. So there are 30 discrete velocities that have to be constructed. We use the characteristic points of the Platonic solids, which have excellent symmetry in space. Here we use the vertices and the middle points of these solids, and we use 8 free parameters to make the model more robust, and can adjust these parameters according to the program. Now we simulate some benchmarks to validate the model. The first one is the more quiet flow. The initial configuration is the viscous fluid between two infinite plates. The plate below is stationary with temperature TL. The top plate moves along the horizontal direction with the temperature TU. And in the figure, the analytical solutions are represented by the solid lines. As we can see, the result of the DBM, which is represented by symbols, agree well with analytic solutions, which demonstrate with different specific heat ratio and with different Prandtl number, which demonstrate the capability of the DBM to simulate the fluid with different gamma and the Prandtl number. Another case is one-dimensional detonation. On the left is the mixture of the chemical product, and on the right is the unbuoyant mixture. The initial condition is given by Rankine-Huguenot condition. The inlet and the outlet boundary condition is imposed on the left and the right end of the domain respectively. Also, the periodic boundary conditions are imposed on the lateral boundaries. The Mach number of this problem is 1.74. Here is the physical quantities of the detonation. The symbol represents the result of DBM, and the solid represent the ZND theory. As we can see, the relative error of these solutions are very small, which demonstrate that the DBM can simulate the supersonic flows, reactive flows. Also, we illustrate the kinetic moments F6 on the upper figures, in the upper figures A and B. Also, in addition, the exact solution of the equilibrium kinetic moments are also represented by the solid lines. As we can see, the kinetic moment reaches the maximum around the detonation front. The physical meaning of these kinetic moments is the non-organized energy in the x direction. The difference between the F6 and the F6EQ is just the non-equilibrium quantity, and is presented in the below two figures. Also, the exact solution of this non-equilibrium quantity is also represented by the solid lines. As we can see, in the reaction zone, the non-equilibrium effects are very obvious. It's this phenomena is physically reasonable because in the reaction zone, the chemical energy is continuously released, and due to the rapid change of the physical quantities, the system departs from its equilibrium state. Also, the numerical simulation, the numerical result of the agree well are in a general good agreement with the exact solution. Also, we simulate a three-dimensional detonation. The initial configuration is the same as the one-dimensional configuration. However, we add a small perturbation to accelerate the instability of the detonation. Here, we add the rectangular and the diagonal perturbation. Also, the boundary conditions are the same as the one-dimensional detonation. Here, it's well known that in the previous numerical simulation and previous experiment, there are two main modes are observed: the rectangular mode and the diagonal mode. In addition, the rectangular mode can be divided into rectangular in-phase mode and a rectangular out-of-phase mode. The most important feature of the three-dimensional detonation is the triple point lines, which divide the detonation front into several parts. Here is the sketches of the motion of the three triple point lines. In the DB, here is the animation of the result of the DBM. Also, we present the snapshots of the three-dimensional detonation of the rectangular in-phase mode. Here we can see the triple point lines are orthogonal to each other and move to the center, and then move collision, and then move to the bore. Also, if we decrease the tube width, we can obtain the rectangular auto-phase mode. The difference between the rectangular auto-phase mode and the rectangular in-phase mode is that the collision between different family of triple point lines are different. Also, if we add the diagonal perturbation initially, we can obtain the diagonal mode. And here are the snapshots of the diagonal mode. To sum up, we have developed a three-dimensional multiple relaxation time DBM for the high Mach number flows. And this model can accurately simulate 1D and 3D steady and unsteady deformations. And in this model, both the specific heat ratio and prime number are adjustable. Thank you. Thank you.
Thank you, Dr. G, for the nice talk. So we have a few minutes for questions, and then we have a coffee break. So if you have any, please.
I have a question from Christophe.
Yeah. I can see it, but I can't see the question, but if you want, you can reply.
Yes, yes. Actually, the hybrid lattice Boltzmann, the hybrid LBM is more efficient than our model because the time step is can be adjusted bigger than our simulation. In our simulation, the time step is have to be smaller than that of the relaxation time. So actually you're right. The hybrid LBM is more efficient than our simulation. Yes. What I mentioned here is that this model lose the simplicity of the LBM. Yes, and I'm not mention. Yes, I just say that this model lose the simplicity of the lattice Boltzmann.
Okay. So now I've seen the question. Yeah, okay. Thanks, Christoph, for the question. Any other? So, okay, if there are no questions, I think we can just stop here for the coffee break. And the next session we start at 4 o'clock in the same room. So see you in roughly 20 minutes. Okay, so good afternoon, everyone. I think we can start with the second half of this afternoon session of complex flows. Next speaker is Alexander Sukov from Think Unique. He will speak about, I can see the screen, regimes of motion of triangular magnetocapillary swimmers.
Exactly. So thank you very much for the introduction and also for making this conference possible. I hope you can hear me.
Yes, yes.
Okay.
Yeah.
Yes. Especially, I mean, for making this conference possible, especially under the pandemic constraints. So I would like to share with you some progress in simulation of magnetocapillary swimmers by means of lattice Boltzmann simulations. So, and this is basically our contribution to the field of microswimmers. Let me a little bit introduce you this topic. I think many of you know, but nevertheless. So the research we are doing goes within the priority, or went within the priority program, because now it's over, on microswimmers, with the aims of understanding biological microswimmers, which are shown here on the left side. For example, different motions of bacteria, some sperm cells motion or motion of plankton, and also their cooperative behavior. On the other hand side, to understand this complex motion of these biological microswimmers, there was a famous article of Ramin Golestanian, where he introduced a simple linear free-beat swimmer, which was capable of swimming and capturing essential physics. And this gave rise to a very broad field nowadays of what is called artificial microswimmers. They can be now of different art and kind. And today, I would like to focus on a particular artificial swimmer, which is a magnetocapillary swimmer. So here I take basically the parameters and the results of our experimental collaborators from Liège University. The main ingredients are pretty simple. You take ferromagnetic particles with sizes of some 100 micrometers, place them at the liquid interface. So basically this is a side view of this interface, air and water interface, and due to their own weights, particle deform the interface, curve it, which finally leads to capillary attraction. To compensate for this, one introduces a perpendicularly aligned magnetic field, which induces in the particles magnetic moment and leads to the magnetic repulsion. If you also introduce a time-dependent magnetic field aligned parallelly to the interface, then as shown here schematically, on the course of one period, one can observe deviations of particles from the initial configurations, and finally some net displacement, such that it means this structure indeed is capable of swimming. What we are doing in this sense is we try to mimic the system in all possible details, such that we simulate the fluid with lattice Boltzmann method. We also consider interface and not just effective interactions. So the interface is modeled within the Shenzhen multi-component model. Also, particles, rigid particles are introduced and placed at the interface such that we have full magnetic interactions, including magnetic forces and magnetic torques. And our interest is not only in static properties like self-assembly, but also in the dynamics. So how the swimmer propagates and under which conditions. And as I said, we try to mimic this situation most closely to the experiment. That's why the fields, magnetic field, time-dependent fields, and also other parameters like distances between the particles, swimmer size in general, and so on, is all chosen closely to the experimental one. So here, this slide shows how this propagation is achieved. So here on the left, you can see that we consider a rather small sized swimmer, such that the distance between each beat is pretty small. And on the right, you see the motion of a larger swimmer, such that all this condition can be observed. And to quantify the motion, we were initially interested in the velocity or propagation speed of the swimmer, defined as the average of all three beats. And we use here relative units. So to say, the time is expressed in units of translational cost, viscous time, meaning that this is the average time which is needed for one particle to relax in a fluid. And the velocities are expressed in diameters per this time. So what we observe is indeed the motion is very pronounced, even not much depending on the size of the swimmer, which is denoted by L. So this pronounced motion is centered around the... Yes? Was a question?
No, I don't think so. Okay, you can go.
Yeah. Exactly. So the motion is basically centered around the inverse viscous time, where we get really high velocities. However, also at low frequencies, some motions, especially for smaller sized swimmers, can also be observed. So in this regime, of course, the propagation speeds were fine. However, at these parameters and latest Boltzmann units, still the temporal resolution was relatively poor, and especially at low frequencies. So here and below, we typically obtained problems. So one of the problem was that it's shown here by this movie, by real simulations, is that when you start apply fields at low frequencies, that in many situations it led to sinking of 1 or 2 beats, basically meaning that the swimmer is destroyed. So one of the reasons for this is that if you take a look at the numbers in the experiment and latest Boltzmann simulations of the surface tension force to the magnetic force in the dynamical mode, this is very important. So of course, we have chosen these parameters before doing statics of 1, 2, 3, and so on swimmers beats to construct the swimmer. We never experienced this effect, but in the dynamics, in the dynamical regime, we always face this problem. So by comparing these ratios, surface tension to magnetic force, we realized that actually in the experiment, this value was really huge, meaning that the dynamics was dominated by the surface tension, while in our latest Boltzmann simulations, these forces were comparable. So one way, of course, would be, for example, to increase the particle size such that effectively increasing the surface tension and to improve the resolution, but this typically leads to enormous computational times. And what we did in this case, we tried to optimize this ratio in a different way, such that we reduced some components of the magnetic forces. Another problem was, if you carefully take a look here on the left, again, our latest Boltzmann simulations, more or less for the same parameters as in the experiment, you can clearly see that although we obtain a motion, in experimental situations, the motion is totally different. So we witness sizable rotations of the beats and also of the whole swimmer, as can be seen here. So then this, of course, led to the this led to the questions why it appears. So, and in the situation where we modify the ratio of the surface tension to the magnetic forces, by doing this trick, we were able to simulate this dependence in a much broader range of frequencies, such that not only centering about this inverse cosine or viscous time, but also going sufficiently to much lower frequencies, and the swimmer remains stable. So, such that by doing this optimization concerning surface tension within Shenzhen and magnetic forces, it's possible to go to lower frequencies. How we explain this, of course, the behavior, especially at very low frequencies, is pretty complicated. But a very naive, a simple estimate, for example, if you extract from our magnetocapillary potential its strength K, so basically the strength of the effective spring, and estimate this value, which refers to the frequency of the spring, of this effective spring, and also the inertia of the beats, then we estimate that this is exactly approximately in this regime. Of course, in our simulations, we have much more complicated situations, such that the interface also make contributions, that the magnetic fields contribute in a non-trivial way, and we have several higher harmonics. That's why we have coupled and very broadened peaks. But the essential physics is captured here, and also, of course, if you increase the size of the swimmer, L, meaning that the hydrodynamic interactions between the beads become less prominent or less sizable, then we get an overall decrease of the simulated velocities. Another step towards how to properly describe the experimental situation, or maybe to modify our simulation such that to better mimic the experiment, is if we introduce such characteristics like vertex angles, which are simply the angles built by lines connecting the particles within the swimmer at all times, and the orientation of the swimmer, which is simply the angle between this the direction of the swimmer and one of the axes, in this case Z. So in experiment, this theta behavior shows a very clear and pronounced harmonic oscillations, basically following the changes of the magnetic field. In the mode at low frequencies, if you look at this, we have some reorientations of the swimmer, but they look rather non-systematic. So what is still then missing in our case? And then in this case, we started to find out the reason for this, and our experimental colleagues performed pretty interesting experiment. So they put a single bead, single particle, so now it's not a swimmer anymore, just a single particle at the interface. This is a top view of this experiment, and then they switch the magnetic field from a certain direction to the anti-parallel direction. So basically flipping it by 180 degrees. So what happens is shown in the movie, but also the trajectory of this is shown in this figure. And you can clearly see that the particle reorients itself. So if it would be only purely paramagnetic contribution, meaning that the magnetic moment is caused by the field, it would lead to the zero for the cross product, which causes the magnetic torque. These experiments indicate that there should be some constant internal magnetic moment in this system. And we we modify the model such that we keep the induced magnetic moment as it was before. So this is caused by the external field, but this is constant, and constant in its strength and constant in its orientation, to again try to mimic the experiment. And if you do this, indeed, we are able to reproduce the reorientation of the swimmer similar as in the experimental situation. And moreover, this reorientation fully follows the direction of the total external magnetic field, and it also follows its frequency. So now I just summarize. So basically, by performing these lattice Boltzmann simulations for magnetocapillary swimmers, for having the Shen-Chen model and full magnetic interactions, like magnetic forces and torques, we identify three modes or three regimes. In the regime of high frequencies, it's possible to observe motion. However, the amplitudes of each beat of motion or deviation of each beat from the equilibrium are pretty low. In the regime of low and intermediate frequencies, where the frequency, the interface should be modified, so the effective surface tension should be introduced, we're also able to see the motion, and now we start seeing more sizable motion or deviations of each beat. However, even in this mode, the situation was not exactly similar as an experiment, and reconsidering of the initial assumptions was needed, such that not only the paramagnetic contribution, but also internal constant magnetic moment should be introduced to cause such intensive reorientations of the swimmer observed in the experiment. So here I'm basically at the end. I hope I could convince you that also for these artificial microswimmers, one can do a lot of interesting things. And in particular, it's really possible to mimic magnetocapillary swimmer within lattice Boltzmann simulations. So starting at the situation where only paramagnetic particles or paramagnetic properties were introduced, we obtained a motion, but which was different from the experiment. Modifying the interface led to low frequency behavior without sinking anymore. And finally, introducing small contributions to the beats, we were able to describe at least mimic the experiments more closely. So with this, I would like to acknowledge the priority program for funding this research, especially also Supercomputer Center in Jülich, and also our collaborators, experimental group of Professor Van der Waal from Liège University and theoretical group of Anna Smith from the Friedrich Alexander University in Germany. And with this, I thank you for your attention.
Okay, thank you very much, Professor Sukov, for your nice talk. So if there are questions, we have time for...
Yes, I have one question. Can you hear me?
Yes, yes, I can hear you. I cannot see you.
Okay. I have a question about the, first of all, thank you for the presentation, very nice. I have a question about what do you think is the mechanism of the motion? Is because of the relative motion between the three particles in the triangle? So if you could fix the distance between the particles, would you still observe this motion of translation?
So the main motion or the main mechanism, I don't show here the results which so parallel to these simulations, we also intensively collaborated with people from Erlangen, and they use so-called bit spring model, such that they, of course, simplified the whole problem in the sense that they didn't have interface and they didn't have, so it was basically a bulk liquid filled, with particles connected via effective springs. And doing low Reynolds hydrodynamics, or let's say expansion for the displacements in this case, they show that the main mechanism in this case is that if you have the springs, then the leading frequency or the leading, let's say, the main mechanism would be due to the springs. So one of the main frequencies would be proportional to the spring over the inertia of the beats, for example. In our case, of course, we see much more complicated behavior, as I said, because we really consider the interface, the way how we apply magnetic forces is not just straightforward. We apply actually fields, and from the fields, the magnetic forces and torques are deduced, recalculated. So to answer your question, I think the main mechanism is in this case due to this magnetocapillary potential and deviation from it. So if you kick the system out of equilibrium due to this break in the symmetry, the system starts to propagate, reorient. But in our simulations, we see much more than this. So it really shows how complex this is.
Thank you.
Okay. Okay, let's thank again Dr. Sukov for the nice presentation. I think we can move to the next one. So 1 second, that I give you the rights to share the screen. So the next speaker is Otmane Awane. Please correct me, the pronunciation is surely wrong.
Oh, that's correct.
Okay, okay, good to know. from Ulick. So yes, I think we can share the screen.
Sure.
And try.
Okay. So
You should have the right. Let me. Yeah.
So, okay. Could you see my screen now?
Yes. Now.
Yeah.
Yes.
Perfect. Okay. Great.
Okay. The title of the talk is inertial migration and particle soldering in cylindrical channels. So,
yeah,
please.
Thanks a lot for the introduction. So, last year I was talking about deformable particles, so about the rheology of deformable particles in a shear flow. This year I'm going to talk about a new project that I pick up, and it's about basically particle transport in cylindrical channels and the effect of Reynolds numbers and the Wormsley number on the spatial distribution of the particles.
Ottman?
Yes?
Sorry, can you swap your displays? We see the speaker's view.
Oh, okay.
Click on swap displays just to the left of your mouse pointer.
Oh, perfect. Sorry, I had two screens, so I guess it's sorry, perfect. Thanks. Okay, great. So this problem actually started from the 60s with an experiment performed by Zeger and Silverberg, where they had what I would call a macroscopic experiment because it's on the level of centimeters. They had basically a long cylindrical channel. They put particles inside. They impose a parabolic flow at high Reynolds, well, I would say moderate Reynolds number, so it's around 100 Reynolds number. And then they observed the distribution of the particles far away from the inlet. And they observed a very interesting phenomenon, which is that the particles tend to flow away from the center of the channels toward the wall and form a kind of ring or an annulus. And the radial equilibrium position of the particles is around 0.6 times the radius of the cylinder. And this phenomena for a long time was not really understood. It has important or significant, let's say, meaning for people who works on basically creating microfluidic sorting devices or on industrial levels, basically, but the phenomena, the physical phenomena behind was not understood. So there was a lot of work, theoretical, start with theory, from a lot of people. So it starts with the work of Rubino and Keller, who basically try to explain the phenomena based on the Magnus force, but unfortunately the Magnus force point toward the center of the channel and not toward the wall. Later on, Zafman also tried to explain the phenomena, and he came up with the what we call today Zafman lift force. But this lift force is basically generated by difference of velocities between the particle and the fluid in the flow direction. But it's generating a lift force which is pointing toward the wall. So it could have been the explanation. Later on, after a lot of work from different people, it turns out that basically neither the Magnus effect, neither the Zafman lift force plays a role. Their magnitude is quite low, actually, in comparison to another lift force, which is the shear gradient lift force, which is induced basically by the curvature of the flow. And this lift force is actually pushing the particle also away from the center and toward the wall. And then when the particle is close from the wall, there is a built-up pressure between the particle and the wall, which will generate basically a force that will push back the particle from the wall. And the balance between these two forces will basically give you the equilibrium radial position. Later on, so starting from the year 2000 and onward, there was the development of what we call the microfluidics, or lab on chips, basically. And people did a lot of work trying to create microfluidic sorting devices based on different mechanisms. For example, based on the balance between the lift force and the shear gradient lift force and the wall lift force, or based on the curvature, for example, of the channel. So basically, let's say using the secondary flows to try basically to get some kind of ordering of the particle, either longitudinal ordering or either on the lateral lateral ordering. Then basically afterward, people also developed what they call active microfluidics, so based basically on electrophoresis or magnetophoresis, for example. And in 2004, there was a breakthrough in this field where basically Matas redid the experiments of Zegre-Silberberg for a very large set of Reynolds numbers, and with microfluidics, of course, otherwise he won't be able to do that. And basically he observed something quite interesting, is that at relatively high Reynolds numbers, so roughly 400 and above, he did not only observe one set of solution, which is what we call now the Zegre-Silberberg annulus, but he observed also that some particles will stay, let's say, relatively close from the middle of the channel. So if we see the PDF here, we will see two peaks, one around 0.5 and one around roughly 0.8. So this new peak, or what's called in the literature inner annulus, did not have any kind of explanation. We don't understand the physical meaning of this. So later on, Morita and co-worker did other experiments, but more or less the same experiment as Matas, but they increased the length of the cylinder. And they observed that for a Reynolds number, which is roughly smaller than 1,000, so we are still in laminar flows, this inner annulus, or the second solution, will disappear, so slowly shifting toward the outer annulus. And at the end, you will end up by having only one set of solution, which is the Zegre-Silberberg solution. So it means that this kind of experiments are quite sensitive to the length of the channel. And we define basically the minimum length needed to reach equilibrium by the entry length. And I will be using also this word later on. Then there has been not that many numerical works, surprisingly, on cylindrical channels, contrary to basically rectangular or square ducts. So the few works also shows that there is basically two solutions. So you have a transition, you have an outer annulus, and at some high Reynolds numbers, basically, there exists also another solution, which looks like stable, according to the authors. And that the transition Reynolds number to have basically inner and outer annulus depend also on the size of the particle. And this is also quite important. So for example, for a difference of, for a ratio between the diameter of the particle and the diameter of the cylinder of 0.15, the transition occurs roughly around 400. But if we have, let's say, a difference of or ratio at around 0.1, then this is supposed to happen at 1,200 Reynolds number. So it seems as it's quite sensitive to the size of the particle. But there is no study actually right now that will give us, let's say, a map on basically when this transition occurs. Also, another interesting thing is that this recent paper from the group of Glowinski shows that basically, even if we increase the length of the channel, there is no difference in the solution. So there is a superposition of the solutions, which is a bit different from the experiments of Morita. But well. Okay, so I'm not going to talk too much about rectangular and square ducts, but basically the only thing that I'm going to say about this is that it has been extensively studied, and the solutions that have been found for rectangular ducts are not always applicable on cylindrical channels. So it means that we still don't know that much actually. Okay, so yeah, so as I said, there is a lack of numerical data for pipe flows, either for steady flows or for Wormsley flows, so pulsative flows. The entry length stability of the outer and the inner annulus is still not exactly properly understood. Critical Reynolds number from where we have the transitions from the outer to the inner annulus is also not yet clear. And there are still a lot of things to do in this field. So basically playing with the particle size, the geometry, the volume fraction, and also the elasticity of the particles. And last but not least, basically, there is also the longitudinal ordering that was not properly discussed by the papers on cylindrical channels. So I will start basically by describing the problem. So we work basically with the motion equation. So if I consider a fully developed flow, the equation is written like this. Then if I dimensionalize my equation, then I end up by having two main dimensionless numbers. One is the Reynolds number, which is the ratio between the initial forces and the viscous forces. And the other one is the transient inertial force, which is basically the ratio between the transient inertial, is the Wormsley number, which is the ratio between the transient inertial force and the viscous force. Then the solution, basically, the solution of the Flow equation can be written like this, where basically this is the real part of the right-hand side here, and G0 is basically just the first kind Bessel function of the zero order. And basically, yeah, so this is basically the problem. So I have a cylinder, I have a particle or many particles, depending on what I want to do. I control the initial position of the particle. I fix the flow profile. I change basically the Reynolds number through basically the later on with lattice Boltzmann to the relaxation time. I can apply either a body force or an oscillatory body force if I want to have a Wormsley flow. Then I'm having a no-slip boundary conditions on the walls to have the parabolic flow. So now I'm just comparing here basically the profile that I can observe for, let's say, a Wormsley number, a Wormsley flow with a high Wormsley number. So Wormsley number of 10. So with solid lines, I would have basically the analytical solution, and with the dots, I have the numerical solution with lattice Boltzmann simulations. And basically now, if I compare just basically the maximum velocity to the maximum velocity over time, so the orange basically lines correspond to the analytic formula, and the dots correspond to the simulations. So there is a shift that, if taken into account, then basically the numerical solution and the analytical solution will fit quite well. And this shift is basically just due to the initial condition, because I start in the numerical simulation with zero velocity everywhere. And I need some time to develop the profile. Okay, so this is what it is. And then now, for example, this is an example of a Wormsley number of the profile for a Wormsley number of 2. So this is a small Wormsley number. So it means that the frequency of oscillations are quite small. Now, if I increase the Wormsley number to 5, this is the type of profile that I would have. And if I go to a Wormsley number of 20, this is the type of profile that we will have. So now, if you are interested about why doing Wormsley flows, for example, so in let's say in blood flow around the large vessels, so basically the large arteries, the flow is not basically steady, but is oscillating, and it's a Wormsley flow actually. And one of the let's say objective of the project that I'm working on is to understand the flow behavior around the heart and around the large vessels. Also, there is an importance for this type of pulsatile flows. For example, if you are working on industrial processes which are involving the transport of particles, sometimes people, or people in industry end up by having oscillations, unwanted oscillations. Sometimes they want to remove the oscillations, and sometimes they want to keep the oscillations. So, but there are not that many papers actually on the topic as well. Okay. Sorry, so quick word on the numerical method. So I'm using the lattice Boltzmann method with the Bézier calculation operator. I'm having also particles in my system, and the particles are modeled with a discrete element method, and the coupling between the particle and the fluid is done through the momentum exchange model. So when two particles are close from each other, so below the resolution, the lattice Boltzmann resolution, so we apply a lubrication force. And if the lubrication force is not enough to prevent the collision between particles, we add a Hess potential. So I apply a parabolic flow, as I said, so body force plus no-slip boundary conditions, and I have periodic boundary conditions along the flow direction. So now I will be talking a bit about the results, starting from the single particle case. So if I consider, let's say, a small Reynolds number, whole number of 15, I fix the size of the particle, and then I start with two different initial positions. So 0 here corresponds to the center of the channel, and 1 corresponds to the to where the wall is. So if I start close from the center of the channel, my particle will be pushed away with the lift force. shear gradient lift force toward basically the solution that was basically discovered as a Geisenberg effect. So 0.6 times the radius of the particle. And if I put the particle closer from the wall, it will be repelled from the wall with the wall lift force toward the Geisenberg solution. Now, if I switch to a higher Reynolds number, let's say a Reynolds number of 600, I observe also more or less the same thing, just that the solution is not at 0.6 anymore, but is roughly at 0.8. So it means that when I increase the Reynolds number, it seems that the radial equilibrium position of the particle is going to shift more and more toward the wall. So meaning increasing the Reynolds numbers means that I increase the strength of the shear gradient lift force. Okay, so this is one thing. The second thing that we can observe from here is that the entry length increases with the Reynolds number, meaning that if I have a high Reynolds number, so for example, I compare this case with this one, I need to travel, for example, a distance of roughly, let's say 600, the diameter of the cylinder, to reach the equilibrium position. This is in the case of a single particle. While for a Reynolds number of 15, I only need to basically travel a distance of 400 times the diameter of the cylinder. So this probably could explain why, for example, at some moment in experiments, if you basically do a cut, like in the paper of Matas at 300, you will observe two solutions because he has a suspension of particles, of course. So a solution that will be here, which will correspond to the outer annulus, and the solution which is close from the middle of the channel, which corresponds to the inner annulus. But this solution, as discussed by Morita in his paper, is not stable. If you let the particles travel for a longer distance, and then you take a cross-section of the distribution of the particle, you will find that there will only be one solution. But this is for the Reynolds number of 600 and for a specific size of the particle. Of course, if we switch the size of the particle, probably the scenario will be different. Now, if I try again to plot the radial migration of the particle as function of the Reynolds number for different size of particles, and then compare it with the experimental results from the paper of Matas. So from the gray to the blue, I am basically increasing the size of the particle. So you can see it here, more or less. So gray particles or gray squares means small particle, and blue triangles means a larger particle. So first of all, we have a good agreement with the experiment of Matas for the set of Reynolds number plotted here. And we have also, and this for the different particle size. Then the second observation is, of course, that the radial equilibrium position for the different particle sizes will shift toward the wall while increasing the Reynolds number. So this is independent from the size of the particle. And last but not least, if we increase the size of the particle, the radial equilibrium position will be closer and closer from the center of the channel. Now I will talk about the case of a dilute suspension of rigid particles. So here I'm plotting again the distance traveled by the particle of the radial position of the particle with respect to the distance traveled by the particle for a Reynolds number of 600 and for a number of 37. So first thing that we'll observe is that for a Reynolds number of 600, let's say at an entry length, let's say of 300, I will have two solutions. A first solution, which corresponds to 0.8, and the second solution that corresponds roughly to 0.5. This is again in agreement with the results of Matas. If I let now the simulation run for a longer time, then basically the inner annulus will also shift toward the outer annulus. So this is similar to what I observed for a single particle with different initial positions. So no surprises here. Now, if I go to a Reynolds number of 37, I observe a more homogeneous lateral migration. So to say that if I cut at 300, I won't observe, for example, two sets of solutions. If I cut at 200, I won't say two sets of solutions. So there's only one set of solution at a given time. So it seems that basically this story of having two solutions, so outer and inner annulus, is highly dependent on the Reynolds number as well, and only appear for high Reynolds numbers. Now, if I plot the radial equilibrium position as function of the Reynolds number for the case of a suspension of particle and for the case of a single particle, we see that it matches quite well with the experiments for the same particle size from the paper of Matas again. So there is no big difference between having a single particle or having a dilute suspension. So this is a dilute suspension at a volume fraction of 0.01, basically. So more or less similar to the experiments of Matas. But so we observe the same thing for the single particle case, so that the entry length, so the distance needed by the particles to reach the equilibrium is increasing with respect to the Reynolds number. And that it seems that there is some kind of collision-driven migration observed even for very dilute suspension. So even for a volume fraction of 0.01, I observed that differently from the case of low Reynolds number, I have two sets of solutions which can be basically caused by this collision-driven migration. Yeah, and as I said, we have a good agreement with the experiments. So basically, the entry length basically increases with the Reynolds number. So this is in agreement with the papers of Morita and the recent and the follow-up paper from the same group. That the inner annulus for Reynolds number of 600 correspond to a transient solution, at least for the particle size that I studied in this work. And those results basically are in agreement with both Matas and Morita. They are in agreement with Matas for a small entry length or small travel distance. And if I let the particles travel for a larger distance, then they are in agreement with Morita that says that the inner annulus is just an unstable solution for Reynolds numbers smaller than 1000. So the critical Reynolds number above which the inner annulus for my particles has become stable must be higher than basically 600. So which is the limit here? I didn't really check for higher for the time being. So this is also in agreement with the numerical work of Chow and all. And for a single particle, the equilibrium position shifts toward the center of the channel if I increase the particle size. So this also could be basically, for example, used in a pi-dispersed solution. If we have, let's say, two sets of particles with different sizes, we can basically segregate them into two populations. And this is basically useful for micro devices, for sorting micro devices. Now I will be talking about another phenomena that we observe. In addition to the lateral or the radial ordering, we have longitudinal ordering. So for example, if I have a Reynolds number of 37, I hope that I can play both at the same time. Yes. So if I have a Reynolds number of 37, I let the simulation run for a while. Then at some moments, I will observe basically just the formation of the ring, of the annulus, the Kreiselberg annulus, but nothing more. But if I watch the Reynolds number 600, I have the formation of clusters with different sizes. So for example, in this case, I have 4 clusters and a single particle here. Now, if I try to basically plot the maximum cluster size as function of the Reynolds number, I observe that for a Reynolds number smaller than 100, so smaller or equal than 75, which is here, I observe no cluster at all. And I only start observing cluster for Reynolds number 100 and larger. And that the size, the maximum size of the cluster seems to increase with the increase of the Reynolds number. Now, if I plot the probability distribution function or the probability density function of the distance between the mass center of the particles, for example, at a fixed Reynolds number, in number of 600, I observe that there is a peak at around 2.5. And this is more or less the average distance between 2 neighboring particles. So now if I try to be more precise and I plot the average particle distances, so basically for each cluster, I compute the average distance between the neighboring particles. So for a cluster of 8 particles, I observe that this average distance is around 2 times the diameter of the particle. For a cluster of 6 particles, it's around roughly 2.5. For a cluster of 5, it's roughly around 3. And for a cluster of 4, is roughly around 4. So it seems that, of course, larger the cluster, smaller the interdistance between the particles. Now, one question is, is this cluster effect resulting from some kind of fine size effect? Because more or less this cluster of 8 is actually occupying a large portion of the length of the cylinder. To answer to this question, basically, I took, let's say, I start first by analyzing the cluster of 8 particles. So I will analyze each of these clusters separately. So I'm plotting here the time history of the interdistance between the neighboring particles. And I observe that roughly after, let's say, 400 times the advection time, I observe that the particle all form a cluster with an interdistance of roughly 2.5 or slightly smaller than 2.5. Now, if I compare this to the radial equilibrium position as function of time, I observe that there is no cluster before first having the radial migration. Once the radial migration takes place and I get the radial equilibrium position, immediately after, the particles start clustering. This is similar for all the clusters formed, for example, for the case of Reynolds number 600. And this also can be extended for the other Reynolds numbers that I'm not showing here. So, but now for a cluster of 6 particles, I observe some small bounded oscillations around 2.5. So this is the distance between particles. And then if I increase, if I go to a cluster with less particles, so 5 particles, these oscillations become more consequent. And if I go to a cluster of 4, then it really starts having important oscillations. So basically oscillating between 2.5 and roughly 7.5. Now, in order to basically answer the question about the stability of the cluster, so although we have oscillations, they look stable actually. So now to answer about the stability of this cluster, so to say if I have a finite size effect or not. So remember that when I put in the probability density function for the suspension, I observed that the average particle distance is roughly around 2.5 diameter of the particle. Now, if I took the following experiment, I just took 2 particles. I placed them at a radial position, which is equivalent to their equilibrium radial position. I just changed the distance between the particles. So I put them I increased the distance from the equilibrium. The equilibrium should be around 2.5, and then I let the system evolve freely. And I observed that after some initial oscillations, the particles will converge, or the particle-particle interdistance will converge toward a distance of roughly 2.5, which corresponds basically to the average distance that I observed for the suspension. So this shows basically that this is not a finite size effect, but it's basically the stable solution of this problem. So for rigid particles, as a summary, I observed that rigid particles for small trains located at the Zegre-Zilberberg annulus, and that the clusters are formed shortly after the end of the radial migration, and they remain stable afterward. And that this clustering effect occurs only at a critical number, which is larger than 75. So as an outlook, I only had a bit of time to do some kind of simulations for the Wormsley flow, so for the pulsatile flow. And for the time being, what I observed is the following. This is simulations for a single particle placed at different initial position under a Wormsley flow. So for a Wormsley flow of 2, which is basically just an oscillating parabolic or oscillating parabola, so I observed that the distance, or there is a migration away from the center and toward basically some kind of find value around 0.6. This is similar to the case without pulsation. Now, if I increase the Wormsley number, this is not yet stable, it's not yet equilibrium, but I observe again a migration away from the center and toward a position which is slightly larger than the one I observed for Wormsley number of 2. So there is an effect while increasing the Wormsley number, is that basically for the same Reynolds number, I move closer toward the wall. Now, if I increase the Wormsley number furthermore, so it means that I increase the frequency of the pulsations, and I don't have any more this kind of parabola profile, but I have a kind of flat profile with some bumps around the walls, I observed that there is a migration away from the wall and toward the center of the channel. So this is some unexpected results, for example. So, but it's basically, I need to run this more and do more analysis. So thanks for your attention. And if you have any questions, yeah.
Thank you very much, Dr. Owane, for the nice talk. So we have time for questions, a few questions. So please, if you have any. Okay, meanwhile, I give some communication for tomorrow. So tomorrow again, the plenary talk will be at 9:40 in the morning. The plenary speaker will be Tim Kruger, and there will be the parallel sessions in same time, so at 10:20 in biofluidics and advanced method. So, okay, I don't think there are questions. So let's thank again Dr. Owane for a nice presentation. And okay, I think there is one. Sorry.
Okay, sorry.
There are two questions actually. So from
sorry. The flow frequency.
from Marisol Report from Tim.
Okay. The low frequency cases. Yeah, so basically, to answer Marisol, so at low frequency, it's behave a bit like a rotor, actually. Yes. Yes. And when you say collision, yes, Tim, is hydrodynamic collisions. It's not particle-particle collision in the sense of particle touching each other and going far away from each other. So particles, in my case, are not supposed to touch.
Okay. Okay, let's wait a few seconds in case there is some reply. Otherwise. Okay, so I think we can just stop here. Thank you again, Speaker Owane, and you can close the session here. And so I'll see you all tomorrow morning. So good afternoon, good night, good evening, everyone. Bye-bye.
Thanks. Ciao, ciao.
Ciao.